Welcome to Chapter 2, Part 2. This part will contain sections 2.4 to the end of the chapter. First, let's look at 2.4, and we will be calculating the interatomic bond distances. Look at this polar bear. He forms a bond between two pieces of ice. First of all, we've got to start out and calculate the magnitude of a vector. The length of a vector, r, and here's vector r, is equal to basis vectors a, b, and c, and fractional coordinates x, y, and z. Now we'll take the dot product of r into itself. So here we have r dot r, and that's where r is substituted in here. Is squared, so here's you're picking up x squared a dot a, similarly y squared b dot b and z squared c dot c, and then we have the cross terms, which would be a dot b, and that would be xy, and since the dot product commutes, that is, you can do them either a dot b is equal to b dot a, then you have two of them. You have a dot b xy and a dot b xy over here, so you pick up 2, and likewise for the other terms you pick up 2 for all of the three cross terms. Now we're going to rewrite this equation in a more compact way. This is a very special way. Notice we have in the center here we have a 3 by 3 matrix, all of whose components are only a, b, and c, and of course they are the vectors, and since say b dot c is equal to bc cosine alpha, that you pick up the information for a, b, c, alpha, beta, gamma in scalar form. And this is a very special matrix, which we will call the metric matrix or the G matrix. On the side here we have a column vector, and the column vector is called the coordinate matrix. And over here on the left we have the coordinate matrix, but the transpose of it in terms of a row matrix. And so here's our metric matrix. It's so important we gave it a little bit of a spin. We can also write the metric matrix as a dot product. It's called the diode dot product, and you can see here you have a 3 by 1 matrix, and here you have a 1 by 3, so that when you dot them in you get a 3 by 3, which is of course the G matrix. Here's a question to ponder. The above G matrix is a 3-dimensional. What would the 2-dimensional matrix look like? You write that down. Yes, I think you've gotten it correct. Here is the answer for a 2-dimensional metric matrix. We're actually taking this left corner here. We're omitting all of the C terms, which is in the third direction or the third dimension. If you want to have a 1-dimensional, you'd have just a dot a. Now let's see if we can put numbers on the G matrix. Every crystal has a G matrix, a different G matrix because it has a different set of lattice parameters. So here we have the a dot a would be 5 squared, which is 25, and then 6 squared would be this term here, which is 36, and this term is ab cosine gamma. Cosine gamma is equal to minus a half, so AB would be 5 times 6 is 30, and times minus a half gives you minus 15. So here you have the two minus 15s. Note this is a symmetrical matrix, which means the off-diagonal terms are equal. Now we have to go back and finish our calculation for the magnitude of the vector, and we can write this formula out. We have, this is r dot r, which is the scalar r squared, so we can write that as r with the square root around all of this. So there's the square root, and here we have the G matrix, and here we have the the coordinate matrix X and the transpose of the coordinate matrix X. So that's a really nice way to write things, and it doesn't matter what dimension you're talking about, and it also has, independent of the type of crystal system, which we'll see later, some treatments give different values for each of the different systems, but we don't. Okay, so let's have a question here to ponder. Let's calculate the R of our matrix from the previous, our G matrix from the previous slide, with 5 and 6 angstroms being our, and 120 degrees being our lattice parameters. And here is the length of the vector A plus 2B. So the coordinates are going to be 1 and 2 of this vector. So here we're writing this out. Here's our previous G matrix, and here's our 1, 2. Here you get the 1, 2 from here, and the column vector is 1, 2. This is the transpose of the column vector. When you do all those numbers, R comes out to be 10.44 angstroms. Now we'll calculate the interatomic bond distance. We're not really interested so much as the distance of an atom to the origin. What we're really interested in is interatomic distances. And so we have atoms at 1 and 2, and the vector 1, 2 means it goes from 1 to 2. So we write it as R12. And here's R1, has the fractional coordinates x1 and y1, and R2 has the fractional coordinates x2 and y2. Notice, but all of this is on the same, has the same basis vectors, so A and B are the same for both of equations. So now we take the difference, and if you see here we have, say, R2, and we can say R2 is equal to vectorially R1 plus R12, and if we solve for R12, we get R12 is equal to R2 minus R1. Now we have R2 minus R1. R2 is going to be x2 minus x1 and y2 minus y1. So the we always go from the initial to the final values, and so we subtract from the, we have the final value minus the initial value. Now we take the dot product like we did before, only a little bit more clumsy, but we can put this in terms, you can see the G matrix is coming into being here, and finally we can write this as R12 is equal to the square root of G times the coordinate matrix for the 1, 2 for this vector 1, 2, and the transpose over here. Let's do an example. We'll take our G matrix from before, and now we have two atoms, A and B, at positions A plus 2B and 6/10 A plus 5/10 A, and the answer is that we're going from R, A, B, so we want to go B minus A, so B minus A is 6/10 minus 1, 5/10 minus 2. Here we have 6/10 minus 1, 5/10 minus 2. Our old friend, the G matrix that we've been calculating all along, and here's the regular column of the regular coordinate matrix, and this is the transpose of the coordinate matrix. When the computer does all of the calculation, you don't want to do this by hand, you get R equal to 8.185 angstroms. So now our polar bear is interested in interatomic bond angles. So now we need 3 atoms. So we have 1, 2, 3 atoms. The apex we're going to call 1. That's always put in the center. It doesn't matter whether we say 3, 1, 2 or 2, 1, 3, but the one in the central number here refers to the apex. So we again look at this situation. We have the dot product of R12 and R13 is going to be the scalar products times the cosine of the angle between them. So this is the equation in which we're going to work with. So we need to get the R12 dot R13, and we go through that and we get this formulation here, which gives you the G matrix here, and this is the R12. Notice it's the final minus the initial, and over here it's the 1,3, so it's 3 minus 1. You have to be very careful that you take the final minus the initial or you end up with the wrong answer. So here we have the similar formula, and if we put it in the cosine form, we're solving this equation up here for the cosine. This equation up here we're solving for the cosine, and we can substitute in the G matrix format for R12.R13, and then we simply divide through by our scalar values for each of those vectors. So that's what it looks like. And finally, we'll look at the area, and which is the two-dimensional characteristic of the unit cell, and volume, which is the three-dimensional. And we're going to look at the derivation. In this case, we're going to take E1 and E2, and we're going to write A and B in those components. It's one of the few times that it's very useful to use the orthonormal set. You don't actually have to, you can go through it, but this proof works out very much smoother if you do it this way. So here we're writing A and B in terms of E1 and E2. We have the area is going to be the cross product, and so we literally write out the cross product here, and then when we gather terms we end up with this E1 cross E2, which is going to have a unit direction, and the absolute values of that is just going to be this A1B2 minus A2B1. And if we look at that carefully, we see that's really the determinant of this matrix. So here we get the A1B2 from this term, and the A2B1, that term here. So now we're going to have a little trick. We're going to square it. Now, when you take the absolute value, you could have a plus or minus sign, but if you square these two, if you take the product of these two terms, if they're both minus, you get a plus. If you get both plus, you still get a plus. So the area squared is definitely going to be a positive number. We can interchange the rows and columns in the second matrix. So we have the A2, A1, A2, and we're switching down over here. So we have A1, A2, and B1, B2. And now we have a little lemma, which is a little side proof. We're not actually doing a proof, we're giving a demonstration. The demonstration is that the determinant of a matrix, or the determinant of the product of two, the determinants of two matrices equals to the determinant of the product of the two matrices. So here we're just going to demonstrate it. We have A and B, and then we take the product AB. So it's A times 3 times 1 plus 2 times 2 is 4. So it's 3 plus 4 is 7, and then you do the rest of this and get that matrix. And now we can look at the determinant of A, which is 7, which is 9 minus 2, which is 7. The determinant of B is 3, and the determinant of AB is 21. And this demonstrates, it doesn't prove, but it demonstrates the equality. So now we'll go back to our proof of the area squared is equal to the determinant of this matrix times the determinant of that matrix. So we can now apply the lemma, and we have that's also equal to the determinant of the product of the matrices. And now we can multiply that out, and when we look at those terms, lo and behold, we get the determinant of, you recognize this now as your G matrix. So the area squared is equal to the determinant of the G matrix, or the area itself is equal to the determinant of the G matrix. This is the two-dimensional area. If you bring it up to 3 dimensions, you can go through that proof with 3 dimensions, and you'll see you come out again that the volume is equal to the square root of the determinant of G. So the formula for either the area or the volume has the same formal arrangement. Well, here's our 3 polar bears. Let's keep going and see if we can give an example. Well, let's look at our old friend. Our polar bears like examples. So here's our old 5 by 6 angstrom cell with 120 degrees between the angles. And what is the area of the unit cell? Well, this is not an orthogonal system, and we can just write it right out. We know here's our G matrix. We take the determinant of that and the square root of that, and we get 25.98 angstroms squared. And here's a summary of all of our calculations using the metric matrix. The basis vectors A, B, and C have units angstroms. The metric matrix G has unit angstrom squared. You can just see each individual term is A dot A, so that's going to be angstroms times the cosine of the angle between them. And then the volume is equal to angstroms cubed. That's the way it always is. Well, you have the determinant of G, so that's going to be angstroms squared, 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 and then we take the square root of that and we get A cubed, angstroms cubed. The fractional coordinates of a vector are x, y, and z. The coordinate vector with those fractional coordinates is here, and the coordinate matrix, which is unitless, is these fractional coordinates in a column. The magnitude of r is equal to the xtgx square root. The interatomic bond distance is this formula. And finally, the interatomic bond angle with the vertex atom as 1 will give you this formulation. Notice the 1 comes in each of the terms. Now we're going to give you an explicit example for quartz. You're going to need this because you have to do this for your own